All right, so thanks everybody for coming. We are so excited today to have Joe Berry presenting. Joe is a principal scientist at the National Renewable Energy Laboratory working on halide perovskite solar cells. His PhD work was on spin transport and physics and semiconductor heterostructures from Penn State. His efforts at NREL emphasize relating basic interfacial properties to technologically relevant device level behaviors in traditional and novel semiconductor heterostructures, including oxides, organics, and most recently hybrid semiconducting materials. He leads the DOE Solar Energy Technology Office's Core Technology Program, de-risking halide perovskite solar cells at NREL. He is the director of the U.S. Manufacturing Advanced Perovskite Consortium, a collaboration between universities and the national labs to meet the needs of U.S. companies examining commercialization of metal halide perovskite-based technologies. Finally, he is a principal investigator on the NREL lead Department of Energy Center for Hybrid Organic and Organic Semiconductors for Energy Frontier Research Center. So exploring the basic aspect of hybrid semiconducting materials. So thanks so much for being willing to stop by and give us a talk, Joe, and feel free to take it away.
All right, well, thanks so much for that introduction. It's a pleasure to be at Colorado School of Mines, at least virtually. Get down occasionally during normal times. These are anything but. I will highlight the fact that I am in a battle with one of my colleagues, Joseph Luther, with respect to Twitter followers. So, you know, if you want to see the latest on what we're doing, you can, you know, I do Twitter. It's the one thing the communications folks at NREL tell me I should do that I do. But we also do have this US map, and you can find, I think I have a link later or at the end of the presentation, but if not, it's usa-perovskites.org. And we're having a hiatus for December due to, you know, just the holidays and whatnot. But we have a number of different companies that we work with presenting on kind of their perspective on what's required for manufacturing of perovskite-based technologies. So I like to start out presentations by highlighting the people who actually do the work. You know, COVID has been humbling in the sense that you discover, if you're a person like me, that, yeah, a lot of your job can be done at a desk, but we have really great folks at NREL. You can see some of the people are common across these teams. We also have a number of other people that we work with, both internationally and in Asia and in Europe. Of course, we want to thank the DOE for a lot of their efforts to support our work, both on the basic side, Office of Science, and on the applied side, the Sunshot program, as well as the Office of Naval Research. That'll get some of the work that I'll discuss here. All right, so this is, of course, the chart, the NREL chart. And one of the key things that if you look at all the different materials here that we have, or this is of course the single cell, single junction cell efficiency versus time chart. And if you look at all these different systems, the thing that's common here is that all of these are indeed semiconductors, right? So photovoltaics equals semiconductors. And of course, you know, photovoltaics are a direct conversion of photons into electrons and holes. And, you know, there are a lot of kind of, a lot of the basic physics of the systems is fairly straightforward, but the details really do matter quite a bit. You know, I think as a semiconductor physicist that, you know, PVs are the most sophisticated way to approach solar energy conversion. There are other approaches that I would argue as a semiconductor physicist are inferior, like solar fuels and concentrated solar power, and that would, you know, give any number of my colleagues heartburn, but I'll go ahead and say it anyway. There are challenges, you know, when you think about solar technologies as a portfolio rather than PV in specific, you really need to think about a lot of the other kind of infrastructure that we require, things like grid that ensures dispatchability. There's also the question, obviously, of resiliency, right? Stability of energy production. All of you are students at mines, and of course I won't, you know, insult your intelligence by saying something as silly as, well, the sun only shines during the day. Okay, you only maybe have access to it half of the day. uh, but uh, but certainly the sun is always shining. But dispatchability is kind of a critical challenge. We want electricity energy when we need it, and so that's what dispatchability really means. But with electrical grid and infrastructure, things like storage, we can really do quite a bit. Then when it comes to research, in terms of what it is that people like me do at NREL, well, we do a lot of device physics, but again, the device physics at a fundamental level for a photovoltaic hasn't changed too much. There are some novel quantum-based approaches, and we do work in that area as well. But really what we spend a lot of our time looking at are these new materials. And indeed, that's what I'll be talking about today. There are system level issues that we also look at in terms of how we lay out devices at larger area. And then there are also kind of questions about how we ensure that we have what we call high specific power for some applications, right? If you think about some of the best solar cell materials on this chart up in here, the 3.5 materials, those are what I often refer to as the best solar cells not on the planet, right? That's what you send up into space. That's what allows us to have GPS and all these kind of wonderful things. They are very, very efficient. They're very, very lightweight, very, very thin, but also very, very expensive. And there are efforts to bring them cost-wise back down to earth, but that's another story. All right, so these are semiconductor systems, and this is basically something I like to start any kind of discussion or colloquium with, which is these statements by Herb Kromer, who is the father of the semiconductor heterostructures, because all PV systems are also dominated by the details of the interfaces and heterostructures. So Herb Kromer's lemma is, if in discussing a semiconductor problem, you cannot draw the energy band diagram, this shows you do not know what you're talking about. The corollary is, if you can draw one but don't, then your audience doesn't know what you're talking about either. And it turns out I gave a colloquium earlier or late last month at UCSB, which is where Herb Kromer was a professor for years. And I actually had the pleasure of working a little bit with Herb back in the day. So this is kind of the band diagram for an ideal solar cell. We have, and I would argue pretty strongly that you have an intrinsic area here where you do the absorption of your photons. Then you have, the photon comes in, generates an electron and hole, and then you likely would like to have some selected contacts. There are ways around this, but certainly you need to make sure that the rate of carrier transfer this direction versus, say, this direction is enhanced. But this is more or less what we would imagine to be kind of the ideal structure, and that hasn't changed a whole lot over the years. There are variations on this theme. There are other ways to basically implement an efficient PV system, but I think this band diagram is kind of what we would imagine for the ideal case. Now, there are also considerations in the sense that, we have to deal with the sun that we have. We don't get to use the sun that we wish we might have in order to make a PV device function more efficiently. It turns out if you do kind of anybody who works on detectors will know that your responsivity, right? Your ability to basically, for a semiconductor to respond and generate an electron hole pair that's then captured is very, very efficient if you're right at the band edge, right? Making a device, if the sun was, say, relatively narrow band, single frequency, doing in excess of 80% would be a really doable kind of process. But what we really have is this black body kind of distribution of frequencies in terms of the photons that we see. And as a result, we have to make a compromise, right? If we harvest the energy too high, we basically, or if we use a band gap in our semiconductor system that is too low, then a lot of the photons that are absorbed create electrons way up in the bands that then relax back down, and that's thermalization loss. In contrast, right, if we basically move the band gap up too far, well, then we just are letting too much of the solar spectrum go through, right? So if you can make, and indeed there are some really nice examples of UV photovoltaic devices, organic photovoltaic devices in particular. And so they're wonderful in that they're transparent, right? But at the same time, if you're letting all the light through, then obviously, your available energy resource that you can convert into usable energy is lower. So those are still very interesting for niche applications, but if we're talking about power generation at utility scale, you can imagine that, you know, there's an ideal kind of trade-off here. And of course, this trade-off is basically the thermodynamic limit for PV performance, or the detailed balance limit. And that basically sets this threshold, you know, around 33%. And now this is a list of all the different PV technologies that we have, as well as I've included perovskite on here. But you can see that gallium arsenide is about the highest, although its, you know, location relative to its maximum is maybe a little bit lower than silicon. And if we think about the way a PV device operates, it's obviously a diode, and we have a, well, I'm presuming that, you know, again, you guys are at Colorado School of Mines. We work very closely with you. You all know about NREL as a place to come and work, which I did not know when I was a graduate student. I did not know about that as a place that existed. And so I'm assuming that a lot of these kind of PV things are kind of background material. So I've included them for the sake of completeness, but if you want to dive in, we certainly can. But this is a typical kind of JV curve. And this is your diode in the dark. You illuminate it and you have, you know, this short circuit current, and then your maximum power production occurs somewhere between where you collect the maximum current or the maximum voltage out of the device, and you can draw the equivalent class circuit. But you can see here that, you know, what our overall efficiency looks like is really dependent upon this compromise that we've made in terms of how we're going to dice this spectrum up, right? So there's an obvious way then to go to efficiencies that exceed this particular limit. And one of them is to do multi-junctions, right? If you do a multi-junction, you're basically going to avoid the thermalization losses. You're going to use an absorber that, say, only absorbs in the blue. That blue light doesn't pass to the next cell down, which then harvests the lower energy photons and so on and so forth. And if you look at the NREL chart, right? So you see up here a little annotation that says 6J. So this is a device that's 47% efficient. And it's 47% efficient because it's sliced up that spectra with 6 different individual junctions, which is a remarkable kind of feat of engineering. And so if you want to play in kind of this 30 plus, you know, so while the limit here is kind of 33, how close you can push this limit is obviously limited by other practical considerations beyond just the thermodynamics of the system, right? Losses in interconnects and metal wires and all this kind of practical engineering stuff that if you don't pay attention to will make your system underperform. But if you want to get then to 30%, you really have to be looking at a multi-junction device or looking at concentration. And that's another thing that that is kind of a critical thing when we think about new materials for photovoltaic systems, right? In other words, the ideal photovoltaic material is a material that interacts strongly with photons, i.e. something that's not silicon. Direct gap would be desirable. And then you'd like to be able to do this multi-junction kind of approach, right? To get to the ultimate kind of efficiency. So this is where we start talking about the metal halide perovskite systems. So conducting tin halides were a thing that David Mitzi looked at way back in where I believe this is, I think it's in the patent that's here. Yeah, 1999, so 2000. Now, if we talk about perovskites as a class of material, it turns out like, I'll say like 80+% of the minerals in the Earth's crust are perovskite form, which is basically this ABX3 crystal structure here. Of course, all those perovskites don't matter anymore. Just like, I'm trying to think of what an example is. Just like every tablet is an iPad, right? Every perovskite is now a metal halide perovskite because they're awesome for photovoltaics. So most perovskites with this kind of crystal structure are, in fact, oxides. They've been around for a long time. There's a lot of cool stuff you can do with them. But the metal halide systems, you know, metal core, and then you got these iodide or bromine or chloride kind of in this octahedra, have are unique in the sense that they're completely synthetic. you won't find these out in nature anywhere like you will the traditional metal oxide perovskites. In addition, this site here, this A site that I've drawn as Ma, which as you'll see presently is short for methyl ammonium, can be either a atom or it can in fact be an organic molecule. And then has kind of a motif like you see in this Mitzi paper where they've drawn out, these carbon chain molecules in a little bit more detail, but very similar to this kind of structure. There are also kind of a couple different things you can play with these. Most of the systems that we talk about for solar cells are completely three-dimensional kind of crystalline systems, very conventional in that they're very like things like gallium arsenide and other systems where, if you have a nice crystal structure, you can do a lot of wonderful things. So if these were around in the 2000s, why is it that all of a sudden they're a big deal? Well, this paper, again, is now from 2009, so roughly a decade after the work I was just showing you, and it's by Miyasaka. And the thing that he did, along with his co-workers, was to basically use these metal halide perovskite materials as a sensitizer in a dye cell type configuration. And it was kind of efficient. But the thing that happened very quickly is after this initial demonstration is that the efficiencies of these systems went from kind of 0 to double digits in a very, very rapid, at a very, very rapid pace. Not only that, subsequent work by Giles Eperon, who was a graduate student at the time with Henry Snaith, who was one of Tom Miyasaka's collaborators in some of the subsequent publications, really demonstrated that by tuning this A site with, from methyl ammonium to formamidinium to cesium, that the electronic gap could be tuned quite nicely for this system, right? So you've got double-digit PV performance kind of out of the box, and you have this tunability, which then indicates that you can get to kind of the ideal gap for a multi-junction system, right? If you're going to, there's obviously a compromise to maximize the efficiency of a single junction, and you can imagine that as you start dicing up the solar spectrum, when you're going from 1 to 2, right, then there's kind of an optimal range for those two to be paired at in terms of energy gaps given the solar spectra. As you go to 3, you have a little bit more options and so on and so forth as you increase the number of junctions. All right, so then I joined NREL in 2006. So in 2006, the perovskites, the metal halide perovskites, were not kind of a thing. And since, this first report in 2009, which would have been back here, kind of like a 3% efficient device, very quickly, this initial value is around, I want to say it's like a little over 14%. And then in the last decade, these have gone up to be 25.5% efficient for a single junction. And not only that, given that we have this tunability of the electronic gap, they've also demonstrated that you can pair these not only to make, say, all perovskite-based tandems, which is kind of the thing that I posited earlier, but you can also make a lot of the existing PV technologies that are quite good at single junction operation, and some like silicon that have been engineered to be quite excellent. You can improve them and make multi-junctions out of them because of the tunability of the metal halide perovskite material. And indeed, I guess it was like earlier this year, Helmholtz demonstrated a 29.1% perovskite silicon tandem. So that's more efficient than the limit for a single junction silicon solar cell, period, right? So, as long as you're not going and using, say, so for a photovoltaic device built on silicon, you can now make a silicon perovskite tandem that can do better than that thing can ever do or ever hope to do, right? And that is quite kind of a technical achievement. With that said, there are some other things about the metal halide perovskites that make them compelling. The other thing I should highlight here too, it's one of these things, right? If you sit back and reflect on it, it's just amazing, right? I mean, I've been working on these things for the last, what, 6, 7 years, which represents, a little over a PhD worth of work. And I mean, they truly are an amazing material system. But this 25.5% efficiency represents the highest efficiency for a thin film polycrystalline material. And we've known about some of the other ones that are on this chart for literally, years before I was born. And I'm old. All right. All of that said, it's useful to take a step back and talk a little bit again about how it is we think about semiconductors, right? So, and it goes back to this notion of more being different, and which is this idea put forth by Phil Anderson, but also kind of energy quantization and how we construct orbitals, right? When we have a molecular system, right, we have discrete states and a manifold of states, and then if we basically put them together, right, or atoms together, we go from, say, a two-level system to a manifold of states. And if we go and build out a crystalline system, you've probably all done this toy problem of either the nearly free electron or tight binding model, we get a band structure. The catch is, though, that when we create disorder in this kind of system, we start basically undermining the functional property of the semiconductor, right? Because it's this band structure that kind of makes semiconductors special. And so defects in semiconductors are the things that make them special, if you will, right? If we have a perfect crystalline solid that has no defects, then it's just kind of an insulator, right? It's the defects and our ability to engineer the defects that can add the conductivity to it if we choose dopants. But it's also the thing that can essentially, is the challenge of these materials, in that if you create the wrong kind of defects in the wrong place, you undermine all the functional properties of the material. Famously with silicon, if you have, I want to say it's like, at part per billion level of nickel, you turn a nice silicon material into basically a piece of garbage, right? You change it from a nice semiconductor that has these properties that you can tune and use for things like transistors, and you ruin it. And so all of these different types of defects can have different kind of impacts depending upon the details of the semiconductor. You can have dislocations, we can have grain boundaries, vacancies, impurities, which I was just talking about in silicon, interstitials, surfaces really are extended defects. That's another kind of issue that we have to kind of deal with. And then you can have kind of surface species and things on the surfaces that create all kinds of problems for you. All right. So one of the things that's amazing about the metal halide perovskite systems is that they have this property of defect tolerance. And this is a paper that was done, work by, actually, Colorado School of Mines' own Vladan Stevanovic. And, in a typical semiconductor system like we were just talking about, when you create, say, a vacancy, for example, you'll create deep states in that system. And if you think about what our band structure looked like for our PV device, if I start introducing states in here, you can pretty quickly see how that's going to undermine the primary thing that I want to do in the PV material, right? Because I want to absorb across the gap. I want to basically relax down to the band edge, and then I want to get the carriers out before they can get a chance to recombine. Now, if I introduce states into the gap, that gives me a non-radiative way to recombine my carriers, and that's additional loss because I don't capture that carrier any longer. So in most semiconductor systems, then you need to have very, very pure intrinsic semiconductor as your absorber material, right? If you don't, then you have lots of recombination, lots of loss. The thing that's amazing in metal halide perovskites is that when you look at what happens if you pull a atom out of that lattice, right, out of that ABX3 structure, the defects that you generate aren't actually in the gap. They're either right at the band edges or they're inside the bands. Now, that doesn't mean that they don't still have consequences that we might care about, but it doesn't undermine the fundamental thing that we need for the material to basically function as a solar cell. And indeed, so like I said, this is a very nice kind of paper by Vladan where he walks through some of this. But there are also these calculations. These were done by Jan Fayan at University of Toledo. And you can see he's calculated out all the different kind of interstitials, vacancies, and so on and so forth for the prototypical MAPI, methylammonium lead iodide metal halide perovskite. Now, you'll notice there are some states that sit here in the gap. The catch is that those are not readily formed, right? In other words, in order for me to have these, I have to actually work at it, right? If I don't work at it, most of the defects that are energetically favorable to form are down here or up here. They aren't in the middle of the gap. And that is, of course, kind of the magic. Now, all of that stuff was theory. These are some experiments that we did with Colorado School of Mines, Xerxes, Ken Steyer, who was a graduate student that I worked with when I first joined NREL, worked with him as a postdoc, and now get a chance to work with him as he's a research scientist at Mines. But one of the things we did with Xerxes is that we knew that we could induce defects into the metal halide perovskites by irradiating them with X-ray energy. And so we irradiated them, and at the same time we looked at the photoemission spectra off of those materials, which allow us to kind of track the valence band edge of those materials. And you'll see that, right, it should be MA-PBI3, but we're substoichiometric in the in a little bit in this particular system in the iodide, right? So the lead to iodide ratio, we'd hope it would be 3, but these samples were at like 2.85 or something like this. But as we irradiated it, we could see that we would lose the iodide out of this system. And the thing that was amazing is that the valence band edge didn't move at all until we got to kind of like 2.5. And then we started to see essentially a mixed phase where we had both lead iodide and the methylammonium lead triiodide system. And so this is kind of an actual physical measurement of the defect tolerance. In other words, we're introducing these defect pairs into the system, and yet we don't see any change in the valence band structure. That is to say, we don't see the valence band move, which is kind of a way of validating this perspective that most of these things that we were looking at, which were just down here, we ignored this because we didn't have access to it. Most of that we basically really get no change down here until we do something quite dramatic to the material, and by changing this ratio to something that's like 2.5, right? With lead iodide being what we'd have at you know, all the way out here at this ratio being 2. And then this is also then the valence band edge spectra, and you can again see it, and it matches up with these different regions of blue, green, and yellow. So that was a cool result. So the fact that you have this defect tolerance then makes this a, you know, remarkably good material. And indeed, if you look at the fraction of the detailed balance limit in terms of the voltage, right? So we're making this compromise in the thermodynamic limit. We make the band gap larger, we can get a larger voltage, but we lose current, right? That's the trade-off given this whole spectrum. But as a figure of merit then, the closer you are to the voltage out of your device being equivalent to the electronic gap, the better off you are, right? So a perfect solar cell would have this at equal to 1. And you can see, indeed, the best solar cell materials we know about, like gallium arsenide or gallium indium phosphide, are very, very close to this value. And what's remarkable is the perovskites are also very, very close to gallium arsenide, much higher than a lot of these other systems that we have. There are some variations on perovskites that have lower values. This is a little bit out of date. We've actually closed this gap pretty considerably, but if you look at the things that we're considering for single junctions, we can do really quite well. Absorption edge is also quite strong. Again, that's kind of what you need for a PV material. Now, defect tolerance is kind of a nice property, but there are always, like all these kind of nice properties, limits to this. And again, these are some calculations that were done by Vladin's group. And here you can see that this is the structure that I showed earlier for the MA-PBI3 system. But as we alloy tin in, right, we start destroying essentially the defect tolerance of the system. In other words, that all of a sudden the defects that kind of can easily form in the system are now in the gap or in the region of the band structure that that then undermines the fundamental physical property, functional physical property that we're trying to engineer in the system. Now, this is still useful in the sense that it does give us another knob to tune the band structure of the system. And as long as we manage this okay, but we do have to manage it, we can essentially lower the electronic gap, and that lets us access lower band gaps in the system as well. So I showed you earlier, we could tune it to higher. That's the thing that we do for silicon tandems. But if we want to make all perovskite tandems, we want to both increase one on the one hand and decrease on the other, and the tin gives us an opportunity to do that. And so this is also, from a basic perspective, really shows kind of how the material is flexible and interesting. But it is this defect tolerant nature that really makes the materials kind of, it gives them the opportunity to be a really kind of transformational thing, right? So we have the fact that they're very good absorbers on their own, showed you really good single junction. We've made silicon better than silicon can ever be by itself. We have the fact that the efficiencies are really, really good. And then the other thing that the defect tolerance does in this particular context is it means that we can manufacture it via a lot of different methods that are very distinct, right? PVs are kind of unique in the sense that, it doesn't do me a whole lot of good to have a photovoltaic device that's, say, a 6x6 kind of size, right? I mean, that's a starting point, but then if I am limited to 6x6, like what we say have for silicon wafers, I need to basically string a bunch of those together in order to basically have a photovoltaic module. In other words, the area that I can manufacture this stuff at is a crucial component, and indeed is one of the reasons why thin films, particularly CAD-TEL, is a very efficient and compelling technology, is because it can be manufactured at a very, very large area. The fact that the defects that we form in the material don't impact the fundamental property that we care about for the PV task means that we can make most of the systems that I've shown here through very, very facile manufacturing approaches. Indeed, all of these points here are all solution processed systems, right? All of the single junction record efficiencies for perovskite solar cells are based on solution processed systems. Now, in the case of the silicon perovskite tandems, I believe in that case, those are still based on solution processes, although there's some argument that because of, quite frankly, silicon's deficiencies with respect to absorption of light, there are reasons why we might want to do something like evaporation as well. But we said in our kind of program at NREL that we wanted to do scaling, which is just simply the issue of making things big. And while the perovskites are really amazing and we can do really great things, the manufacturing component of it, there's a lot of science in that too, because it's not simply making things big, it's making things the same all the time. And indeed, if we want to be a successful solar technology, we need to be able to make it really, really fast too, we would argue. This is a printing press at the Kodak facility in Rochester, New York. And we're working with a company there that DOE has funded to basically scale perovskite solar cell technologies. And if we can get this done, this would represent kind of a 2.5 gigawatt production capacity, this one tool, right? And here are some kind of calculations that kind of bring this, back of the envelope Fermi calculations that kind of make this clear. So the opportunity is the fact that we have it's a thin film technology, low cost abundant materials, and we can use very facile production approaches. If you look at what it would take to completely electrify everything with silicon, 25 terawatts is probably a low estimate at this stage, let's say even 30. But with silicon PV production, you take on the order of 170 years. Now, of course, you can accelerate that, but if you think about silicon as roughly $1 billion a gigawatt, right? What we're talking about here is our orders of magnitude decrease in that capital expense. And, perovskite solar cells are now being demonstrated at area efficiencies well in excess of 15%. But if we just say we want 15%, and we can print the stuff as fast as we can print newspapers, which again, we think is, might be a little bit of a stretch, but the company that's working on this tool, I was just looking at some of their materials where they're printing at 70 feet per minute. So, it's a ways off from a mile per minute pace that you'd see for something like the New York Times, but it's starting to get there. But if we could do it at that kind of pace that we print newsprint, then you can really, really quickly get to these kind of terawatt scale production very, very quickly. And we talk about kind of what this opportunity is in this particular article. This is a tool that we have at NREL where we can prototype some of this printing stuff. And this is one of the graduate students with a perovskite roll. This is now, I don't know, probably 2.5, 3 years old. Dak is now out at MIT leading some of their efforts on these technologies. So, perovskites really does give us this opportunity to have high value PV everywhere. We have other people at NREL who are looking at dynamic window applications because these materials have some interesting kind of phase change properties that we can leverage to create systems that when they're, say, exposed to IR, i.e. heat, they basically darken and tint and become more efficient kind of absorber materials. Otherwise, they're more of a UV absorber and they're producing kind of very minimal amounts of energy. We do some work with folks like DoD looking at these kind of applications. We have other companies that are targeting multi-junction all perovskite tandems to displace traditional 3.5s at much, much lower cost for kind of high Earth orbit applications or even indeed satellites and power beaming things. So how do we actually make these solution process systems? So there are demonstrations. I guess I don't know that we've done all of these at NREL, but we have certainly done spin coating. We've done dip coating. We have done doctor blading. These two, spin coating and doctor blading, we do all the time. We've done slot die coating. In fact, that picture of DAC I showed was definitely slot die. The one that's not on here is gravure, which is a variation. Basically, you have a roller that basically picks up ink and puts it down, very similar to what you do in kind of newsprint kind of application. We have sprayed the stuff. We have screen printed the stuff. We have inkjetted printed the stuff. I don't know that we've done chemical bath depositions at NREL, although that is another approach that can definitely be used. Trying to think, not for solar PV perovskites. Now, and of course you can evaporate these things, right, as well. So you can use vapor phase if you're so inclined. This is an article that we wrote a number of years ago that basically talks about the challenges as it pertains to making things larger, what kind of losses do you see in a typical PV system as you go to a larger area. And this shows the PCE as a function of year and as a function of area. So you can see that it's improving. Now this one shows the PCE as a function of area, increasing area here, for perovskite solar cells, and it's black, versus other technologies. So dye-sensitized solar cells, relatively flat here, OPV. And really what we're looking to mimic are kind of things like CAD-TEL, and indeed, we'd like to avoid CIGS. Because CIGS did really, really well until they needed to get to the ultimate size that they needed for outdoor. But we'd like to be up here, we're down here. And so the question is why? Well, this is the other chart that we have at NREL. And when this paper was published, which was 2018, so a number of years ago now, since then, since 2018, this is what the efficiencies of perovskite mini modules as a function of area have done. So you can see here, we're talking about systems between 2 and 800 centimeters squared, right? Relatively modest efficiency is 11%. But if you look at what's happened in the last year or two, it's gone up very, very quickly, right? So now these are basically at 17.9%. And in contrast, First Solar's very, very large area modules are just sitting above that by, a little under 2 percentage points absolute. Now, granted, that's a lot bigger area, so there's a lot of work to do. But I can tell you that I anticipate this being closed very, very rapidly. I know results that the certification group has gotten where I expect improvements on these values here as well. So a lot of the module efficiency kind of issues come from the fact that, right, if we can make very, very good single junction devices, then there's a lot of engineering that we can leverage where people have learned how to make things at larger area. And while there's still lots to do, things are looking pretty good. All right, so in the little bit of time I have left, I want to address kind of the elephant in the room, so to speak, right? Because if you want to be a real PV, you need to have performance. You need to have this manufacturability. And I've argued that perovskites have some unique attributes when it comes to the manufacturability in particular, but performance is really quite good. The last one is really stability, right? Nobody cares if your PV doesn't last for a decade or two, let's say. There have been some nice analysis about exactly how long you need a PV system to really, really last at what kind of performance level. But certainly 30 years is kind of common for silicon-based PV. Part of that is due to the fact that, okay, there's a lot of embodied energy into a silicon-based PV system. In other words, you have to put a lot of energy in. And so the more energy you have to put in, the longer you have to have that device run without significant degradation before you can recover that energy, plus all the surplus that you hope to get, right? So, and you'd like to have it, I mean, general rule of thumb, right? You'd like an order of magnitude ROI on that energy investment, right? And so stability. Now, I've argued from the very beginning that photovoltaics are semiconductors. And we were talking about thin film semiconductors. Now, most of you have cell phones, right? You have thin film semiconductors that you live with all the time. However, I would suggest that most of you would not think that if you took that cell phone out and put it on your roof and let it sit there for 30 years, that it would be working any longer after that time period, right? That is a challenge, right? So one should not overstate this. But at the same time, you don't get to ask the stability question if you don't have the other two, right? If you are not efficient and you are not manufacturable, you don't count either, right? You can be stable as a rock, but if your efficiency is 2%, I don't care, right? And rocks are quite manufacturable, so I suppose that's a benefit to the rock. But this is a perspective that we did a little while ago, where we talked a little bit about considerations for device stability. And one of the challenges here too is that when we think about societal challenges like climate change, right? That's part of the impetus for wanting new technologies, right? We simply, status quo is probably just not good enough, right? To really address kind of emerging energy needs and to go kind of beyond and maybe cleaning up some of the environmental impacts that we've created for the planet in the context of industrialization. So we would like to basically know that a solar cell we make today, I mean, in a perfect world, I'd have a measurement that if I made it in 10 minutes, I would know where that solar cell is going to end up in 30 years. Keeping in mind that for the metal halide perovskites, right, 10 years ago, I didn't know they existed, right? But yet I want a measurement that I can do today that will allow me to predict the future that's in excess of our knowledge of the systems even existing for this application, right? So that's a monstrous challenge, but quite frankly, that's what we do as scientists, right? We take on those challenges because if we really understand those materials, we can make those predictions. And if we really understand the materials, we can also kind of develop and devise tests that allow us to get, maybe it's not a 5-minute test, maybe it's, a 1,000-hour test, but under conditions that really simulate what would be the aggregate kind of accumulated stress on a material over a 30-year lifetime. But this is a saying from Sarah Kurtz, who ran the reliability group up at NREL for many, many years, is that, yeah, you put an egg in an incubator, you get one result. Put it in boiling water, you get a very different result. And so we have to be super careful when we think about trying to do these kind of, accelerated testing kind of protocols, that we aren't basically putting our egg into boiling water, right? We really need to know what the end state is in order to do these kind of tests. Oh, I apologize. It's turned out a little bit foggy, but we talk a lot about in this article about kind of a hierarchy of materials levels that we're considering, right? Or levels of stability. There are material level considerations, right? If a material is fundamentally photophysically unstable, maybe we shouldn't make a PV out of it. So perovskites don't have that kind of problem. But a material is not a device, right? So there are also device level considerations, and we've done quite a bit of work here as well. And how you construct these tests depends upon it's science, right? You have a hypothesis with respect to an issue associated with stability, or a physical mechanism of how the material is responding under particular stresses, and you need to be able to test that. And so, we talk a lot about kind of this hypothesis, stress test, mechanistic insight, and then, we can decide whether or not that warrants putting, say, the material into a device, and then we can do that loop again. And again, if the devices turn out okay, then we can go to say, a module. The thing that's been kind of crazy is how rapidly, this article is I want to say from also like 2018 kind of time frame, 2019. And at that time we said, well, we're restricting ourselves only to this stuff. Well, we're already starting to look in this area now in outdoor tests and at module level. But I do go back to the notion that, all the considerations that we have with respect to understanding the materials are relevant in trying to assess stability because of the challenge of stability at a basic kind of level. And one of these are some slides that Joey put together that I think really kind of, again, highlight this, that if you look at the first practical solar cell, right, we take PCE measurements of solar cells all the time. It's a common thing. Everybody does it. Takes 5 minutes. But if you look at how the first solar cells were reported in terms of their PCE assessment, you would not get on the chart with that, right? That would not hold up to the current kind of scientific standards at all. Not only that, we're asking a very reduced question. We aren't asking the question about how much energy we produce for a module out in the field, which is a much more complicated question. We're simply asking how well the cell actually does. And so in the context of stability, it's more difficult to reduce that down in the same way that we reduce down this power conversion efficiency. Because stability is like I said, it's not as simple. In the case of efficiency, right? Power in versus power out is kind of what I want to know. That's at a basic level. In the question of stability, what do I really need to know? Do I need to know, how slow mechanistically things are, right? What the kinetics are? Do I need to know, say, maybe these defects that I talked about before, right? That don't impact my ability to make a very high PCE, do impact my ability to make a device that lasts for, say, 15, 20 years. So these are kind of the open questions. When we think about where the instabilities are really at in the devices, a lot of what we're concerned about are at the contact interfaces. Now, there are questions about the active layer, particularly though, I showed that by alloying lead in with tin, right? The tin kind of undermines this defect tolerance of the system. And so there are questions about the active layer and how well we can manufacture that and make it, and whether or not some of those defects that we don't think impact, say, just pure raw PCE, may be impacting things like overall stability. There are also questions about, say, what the interactions of packaging looks like. But for the most part, a lot of what we do are targeted up here in terms of these interfaces and contact materials, getting those right. And then, there's kind of a learning curve that we're kind of perpetually going up on the perovskite active layers. And indeed, it's a true statement to say that when you make the materials more efficient, you tend to make them more stable simultaneously. So that's a good thing. One thing that I'd highlight, if you're really interested in this question about, how we think about now, more recently, kind of understanding the details of the materials in a way that informs how we think about stability problems, I would refer you to, here's this is the same same graphic from the previous work that I mentioned, but you can actually read it now. But this is a review paper that a graduate student working for me, Sean Dunfield, put together that does a really nice job of going, from defects to degradation. It really kind of walks through what we consider at the moment to be key questions that we need to address. That said, one of the last things that I want to show you guys is kind of where we were when we first started the metal halide perovskite efforts at MREL. So this is basically our normalized device efficiency for a set of devices. So you can see our devices were not very similar across the set, and they lasted for maybe 5 hours, maybe, kind of, sort of. But we did some things in terms of looking at our contact materials, and we made the devices more the same. And so now we can last for a whole day, right? That was what we did. And then a little bit later, we did some things where we modified going from the pure MAPBi3 system to alloying the formamidinium and cesium into that as well. That gave us some other, that changed some of the defect structure, but also changed some of the band structure in ways that were advantageous. But that seemed to improve things, and now we have things that last kind of 150 hours. Still not very good for a solar cell, but then we did some work with Alan Sellinger at Colorado School of Mines, because we identified this transport layer in our material, or on our device stack. This material had some issues, and we replaced it with a different organic that Alan had experience making. And now, okay, now we're starting to look like we've got something, it's at least above 60% after that 150 or so hours. But, we removed the gold and we went back to this contact in combination. And again, now we're at 500 hours. And I should mention, these are all for devices under constant operation, room temperature, kind of 25 C-ish, but no encapsulation. So just like in the lab. And so this was better. But then we basically figured out that this little bit of reduction that we're seeing here was really coming from the other contact material, the titanium. And by addressing that interface in combination with all these other interfaces, now all of a sudden we had systems that could go for 1,000 hours unencapsulated, constant operation at ambient kind of temperature. And this was a result that we published in Nature Energy a number of years ago now. And really points to the fact that the interfaces were a critical component. Not only that, we, on establishing the fact that we were pretty sure we had engineered all the interfaces appropriately to cut off some of this electrochemical redox and some other issues associated with lithium aggregating water at our interfaces, we could basically go ahead and swap out the different active layers through a range of kind of different compositions. And these things are all nice and flat over kind of the course of, I think this is like a 700-hour test. But then I think we pulled this one short because apparently Excel didn't want us testing any longer before they turned off the lights on us. But that's. We've subsequently done tests where we've gone for a little over 5,000 hours. In this case, we do isolate the devices from known degradation associated with water, right? These metal halide systems are kind of salts. And so if you let water get in there too much, it creates some problems for you. Although for the compositions that we're using, there are some ways of recovering it if they do get hydrated a little bit. And we subsequently demonstrated for DOE, we've repeated this kind of demonstration of over 5,000 hours for systems both at elevated light intensity and at elevated temperatures. So we feel pretty good about that. But when we think about modules and making things bigger, all of this work and all of the stability improvements that we realized were really by engineering the details in the interface. And when we go to a module, at least a monolithically interconnected module, what we do is we create a lot of uncontrolled interfaces that we now have to go back in and deal with. And this is something we're actively kind of researching on. And with that, I think that's kind of like where I'd like to end. I mean, I've taken up an hour. We're doing a lot of cool stuff with tandems and other stuff too. And And yeah, we're generally pretty happy with the progress we're making. We do a lot of work with industry, and I do think that, you know, the way I put it is that one of the reasons why I'm still at NREL after a decade is that I work on these systems, and you don't get many chances to change the world every day. And every day that I walk into the lab, or indeed just go to Zoom meetings, as it turns out, I often do these days. There is an opportunity to really kind of make a difference in how we generate energy. So with that, I'll thank you for your time and attention, and I'll maybe find a closing slide that thanks some of the folks who've been through our program here. These are some of our former postdocs who've done some of the work that I showed you. Philip here worked with me, and this is the French President Macron. He got one of these Make Our Planet Great Again awards about 4 years ago now. So if there are any questions, I'm happy to answer them now.
Awesome. Wow, that is incredible. So I have a quick question, selfish question that you probably answered. So the last devices that you were talking about, were those multi-junction devices, or were single junction?
Those are still single junction. So we have, there was a Joule paper that we published where I think we put so for all perovskite tandems, right, we use tin. And when we use tin, we really do create some other stability issues for ourselves. We have done all perovskite tandems. I think we've gotten something on the order of 500 hours on those, or so. But we have really good device results for silicon perovskite tandems. Some of those results were reported in Science this past year, as well as some perovskite CIGS tandems. So for our wide gap systems, which are very similar to the single junction ones I was showing you, the stabilities there are quite good, right? We can really engineer those quite well, and they're very analogous to the single junction. The single junction is maybe a little bit trickier from a stability perspective, maybe, but they're very similar.
Okay. Awesome. All right. So anybody else, sorry, I didn't mean to jump in to be the first person, but if anybody else has questions, you can raise your hand. I'll promote you to panelist. Or
Joe, this is Ruben. A new material like this, people would be looking at other applications for it, especially this optically active as it is. What's going on in that area? LEDs, X-ray detectors, things like that.
Yeah, that's a great question. So in our EFRC, we kind of look at a lot of stuff that is not PV. And in fact, I have a whole nother talk that, but certainly LEDs is something that we're looking at. And there are a number of, to be honest with you, we're kind of behind on LEDs. As phosphor materials, the PLQEs that you can get out of these are very, very close to unity, extremely close to unity. So they're wonderful materials from that perspective. X-ray detectors, there's been a lot of reports as well of some really compelling results on X-rays. I have a postdoc working with me actually right now, looking at that particular application and looking at how we can engineer the materials. But basically, yeah, it looks like there are really fabulous opportunities to improve kind of what kind of responsivity you get out of X-ray detectors by a factor of actually close to 100. So you could tolerate a lot of degradation and still be a factor of 10 ahead. That could really impact medical imaging kind of applications or homeland security kind of things. So those are definitely things that we're looking at. There are also some really interesting things you can do with the organic components of these systems. So while there aren't very many organic molecules that fit in that allow you to make this 3D structure, if you go and make, if you use a slightly larger cation, A-site cation organic, you'll create systems that are essentially layered compounds, so like multiple quantum well type systems. And those can have some very fabulous optoelectronic properties as well. And there we can actually introduce chiral molecules that can allow us to get spin selectivity in those systems as well. So that we can create spin transport and spin injection kind of systems in a semiconductor that are really, really cool. So I'd encourage you to go ahead and so this is the EFRC website, and it highlights some of the stuff that we've been doing in that particular area. But yeah, I'm definitely one of those people that believes that if you're going to spend all this money doing R&D on on a semiconductor, it ought to be good for more than one thing. And so these are, and to be perfectly honest, part of the reason why I was put in charge of the project is because I was kind of like, I had a discussion with one of my good colleagues, Ingrid Reppens, who had survived the CZTS efforts, let's call them, where, you know, those materials seem to have some fundamental defect structures that just, you know, are problematic for high efficiency. And so my goal was to really kind of figure out, is there something that's a problem with these that will never let them do what it is we're hoping to do? Because if there is, the sooner we find it, the sooner we can move on. But, and that was my perspective. But at the same time, I thought, well, these are really kind of just fantastic materials, because I've been doing some of the organic stuff. My background's in, proper semiconductors like gallium arsenide and 3.5s. And so this was kind of the Goldilocks material, right? It's kind of like an inorganic. It's kind of like an organic. And so it's kind of got the Goldilocks just right thing where you can really tailor a lot of the materials properties. So I thought it was just a fascinating system to look at. And I figured, well, if I spend my time working on this, it won't be a waste of, and they aren't good for PV, it won't be a waste of my time.
Right.
But,
no. Awesome. So we have a couple more questions coming in if you're up for it. So we have a question from Meadow that says, Meadow says, thanks for the great talk. Sorry if I missed it. What's causing the breakdown over time, particularly in the early cells that lasted fewer than 100 hours? Is it mostly reactions with water, or is there some other mechanism that's going on?
Yeah, I mean, so if you look at the MAPI system, right? So the MAPI system is the methyl ammonium can volatilize, basically, right? So it's a nice material because it's room temperature phase is single phase and is a really nice semiconductor. But at room temperature, the MAPI can essentially, you can lose it, right? The MA can come out with the iodide and it'll volatilize away. Now, that's a problem for a thin film, obviously. But when you put it in device, there are some compelling studies that show that there are tricks you can play in the device stack to not let the methyl ammonium essentially volatilize out. But in our stacks, we didn't introduce any kind of strategies to prevent that volatilization. And when we moved from MAPI to the FA doesn't have that problem any longer. It's not able to volatilize out, and neither is the cesium. Now, in the case of the FA, it has two competing stable phases near room temperature. And so we have to manage the phase stability of that material. And the cesium basically allows us to tune and manage that, right? So if you put the cesium FA together, that allows you to basically modulate these two phases. And then you add in a little bit of the MA to basically kind of get the mixture right. And we have a nice paper on basically the thermodynamics of mixing and stuff like this related to these systems. So initially, part of the reason why those things were falling apart, well, the other thing that was a real problem is that the gold does chemistry with the active layer. This is stuff that we've demonstrated kind of more clearly. It was shown in the literature by the group from EPFL that gold would migrate through the stack, but it turns out it's an electrochemical reaction between the metal and the perovskite, that if you drive it at too high of a voltage, there's electrochemistry that basically pulls that stuff right through. And then that was creating a lot of issues. So a lot of the contact layer kind of stuff was critical in addressing those kind of interfacial redox reactions. Hope that answers the question.
Yeah, I think so. So, I mean, are you basically saying that in some of these devices, they would just evaporate?
Well, you would lose, so they would go, you would lose the component that keeps you in the right structure so that you can interact strongly with light. So in other words, you'll lose the gap. You'll lose your band gap. It'll go wider and wider and wider, basically.
I see. So one more here we have from Alan.
Lead toxicity.
Yeah. Yeah. So how's the toxicity
lead
of
toxicity?
Lead hindered advances in manufacturing?
Okay. So all right. So I can give the flippant answer, or I can give the deep dive answer. I can give every kind of answer in between. So can you give me a little bit more color about what you're really concerned about, Alan?
And actually, let's just see if Alan wants to. ask this question live.
If you can give me a little bit more color, I can kind of tailor my answer.
Yeah, Alan, if you just want to actually ask your question verbally, we can go that way.
Hi, Joe. Yeah. So
Oh, hey.
it's just a, it's just a common thing a lot of people talk about. So from the manufacturing side, which I haven't been a part of as much, like what goes wrong, or how is like our companies like afraid of lead basically for all the health concerns? That's all I meant.
So it turns out that from a manufacturing perspective, some of the solvents we use are a bigger concern than the lead. So that provides some contextualization. Some of the solvents that we're currently using, actually, we just had a manuscript accepted at Nature Sustainability where we looked at solvent kind of considerations at manufacturing scale. And those are the big drivers of the health and human toxicity kind of impacts. Lead is obviously, it's a heavy metal. It is something we have to be concerned about. But if you look at how much we use in these thin film devices, it's not terribly significant. One calculation that I did, I've done this calculation a couple times. I have some slides, but I didn't put them in this deck. But if you look at the amount of coal, so lead's residual in coal, right? And if you look at the amount of coal we burnt in the US in kind of a typical year, like 2015 or something like this, there was enough residual lead in that coal to represent a terawatt worth of perovskite thin film PV, right? So, so the lead issue is not a big issue. And indeed, if you look at a lot of kind of industrial processes we use for making things like TVs can represent a significantly more toxic kind of manufacturing process than what we'd imagine for these kind of solar cells, even at large volume. Plus, when you look at kind of the overall bill of materials and things, the lead component just isn't typically that worrisome to most of the industrial entities. Now, that is not to say that one can just pretend these things don't have lead, right? Organic solar cells are still going to be better if you want to integrate kind of a power source directly in your kids, stuffed animal, right, or smart stuffed animal type thing, right? Because you don't want to eat this stuff. But we have developed some technology that really, and I should also say the lead is special. If you don't have the lead, you don't have this kind of orbital structure that creates the defect tolerance, right? That's what I showed with the tin. So the lead is special. The lead is kind of magic. But in terms of basically lead leaching out of these systems and into the environment, it's fine to say that globally it's a net benefit, which is kind of what I was saying in the context of the coal argument. But if it's on your roof, you're still going to care, right? Because you don't want to have your own Superfund site. So we have developed and are continuing to develop some very nice kind of layers that we can introduce into the device that chelate the lead, given its form. And we've demonstrated that then if you do that, you just don't get any leaching out. There's other researchers out of, I want to say California, I think they're maybe Berkeley, have done similar kind of tests for fire. Now, fire is a little bit of a concern, right? But if you're using a glass package, it seems like you're well below kind of the standards that you'd be held to with respect to toxic release kind of considerations. So I hope that answers the question globally. We've thought a lot about this. We looked at it. We do take it seriously, but at the end of the day, it's more of a perception management issue than it is a real technical kind of health and human toxicity hazard, if you will.
Yeah, great. Thank you.
Awesome. Maybe one last one here, and then I think I'm going to call it. So John Rose asked, and I actually had the same question, so I'm glad that he asked it. For the greater than 1,000 hour stability test using the improved interface materials, the efficiency actually seems to increase for the first 100 hours. Is there some kind of burn-in or something that's going on?
Yeah, so that's an accurate observation. So So the way we do our operational tests, right? So there are a couple different ways that people do it. The way that we do it is we do we operate the device under load, and then we do periodic JV sweeps. Now, these materials, these halide perovskite materials, do have mobile ions, and those mobile ions need to be, will be modulated inside a device. Now, as we're making better and better materials, the amount of, or the number of those mobile species seems to be going smaller, being reduced. But given the polarity of the device, then on the initial few sweeps, we often see this kind of light burn-in kind of thing. And in our case, since we're doing the JV sweeps, we're actually depoling the system. So in other words, if we did like maximum power point tracking, we'd actually see that rise more quickly and it would level off more rapidly. But since we do periodic JV sweeps, we're kind of like resetting the system as we're basically letting it evolve a little bit. So that is something that that does happen in these particular devices. It's something that it's not as prevalent as it used to be. I talk about, so there's, oh man, I should have pulled it. Joey Luther has a slide that's really great. Like if you look at the number of publications per year in perovskite photovoltaics, it's unreal, right? So we have this thing we call perovskite time. It's kind of like an accelerated test, right? All of us get older faster. So if you look at how rapidly the technology is advancing, things that happened like 3 years ago that I present like in the context of a colloquium really are old relative to what we're doing kind of in the lab today. So, we've done additional studies with Alan Sellinger and working with our team where we're able to do similar kind of tests like what I showed, but now at elevated temperatures like 70 C. So things are moving along quite quickly, but I hope that answered the question. There are some of these ionic species have to basically find their home early on, and in a way that doesn't create any other side effects or interfacial chemistry that's bad. But all right.
Yeah, thanks so much, Joe. This was a totally awesome talk. I actually learned quite a bit from it. So yeah, we really appreciate it.
My
and
pleasure.
I think with that, I'm going to go ahead and stop the recording. And
all right.
Thanks, Joe.